So let's talk about Lord Kelvin, who did an experiment where he changed the temperature of a fixed mass of gas and measured the corresponding volumes. He plotted a graph and noticed that it was a linear relationship, that is, a straight line graph was obtained. From this, he could predict volumes of gas within the range of his experiment, which is known as interpolation. A more formal definition of interpolation is when you get values within your graph that are within the range of the experiment. So if, let's say, for example, this particular experiment was only done from about -10 degrees Celsius to about 100 degrees Celsius, when you can make predictions about the volume of the gas within that range of temperature, that is known as interpolation. So let's say, for example, if you wanted to know what the volume of the gas would be when the temperature was 50 degrees Celsius, you would start and you would mark a vertical line from 50 degrees on the temperature axis, which is your horizontal axis, all the way up till you meet your line of best fit, and then you make a horizontal line over to the vertical axis and you read off that corresponding value. So for example, if let's say the temperature was 50 degrees Celsius, it would correspond to a volume of 2.5 cubic meters. So even though it was not one of the points that were plotted, one of the actual values read from the experiment, you could make that prediction with some great degree of accuracy. On the other hand, if you wanted to make predictions outside the range of your experiment, you would have to extend your line of best fit, and this is known as extrapolation. When you extend your line of best fit, you don't normally extend it with a solid line. You would extend it using a dotted line to illustrate that it is not within the range of the actual experiment that was conducted. So Lord Kelvin extended his line of best fit to the horizontal axis, where he logically surmised that the volume of the gas would be zero. He thought that this would be the coldest temperature possible because the volume of the gas could not become anything less than zero. In other words, it could not be negative. So when Lord Kelvin extrapolated his data, he found that the coldest temperature possible would be about -273 degrees Celsius. And he called this absolute zero. He called it absolute zero because it was absolutely the coldest anything could be in the universe. It was not a virtual zero like on the Celsius scale where you could get below 0 degrees Celsius. This was absolute zero because you could not get below 0 Kelvin on his newly invented scale. Charles' law, which is named after Jacques Charles, a French fella, not to be confused with Jack Charles, a born-again black fella, or worse, James Charles. So Charles' law states that for a fixed mass of gas at constant pressure, the volume of the gas is directly proportional to the absolute temperature. So first off, let's look at our constant variables. There are two of them. What must stay the same are the mass of the gas and the pressure. So in other words, it has to be in a sealed container, and the pressure, the atmospheric pressure, has to stay the same outside of that container. Once those are set, then your manipulated variable is the temperature, and the volume is then the responding variable. So if you were to plot a graph, you would see that you would get a straight line graph that passes through the origin. Now, key thing is also to note that it is the absolute temperature, the temperature that is measured in Kelvin. Only when the temperature is measured in Kelvin will your graph pass through the origin and be a straight line. When the temperature is measured in degrees Celsius, then it will still be a straight line, but it will not pass through the origin of your graph. So now we will look at a couple of examples of calculating with Charles' law.
A hot air balloon has a volume of 2,800 meters cubed at 99 degrees Celsius. What is the volume if the air cools to 80 degrees Celsius? We'll write Charles' law in the before and after form. V1 over T1 equals V2 over T2. We substitute in what we know. Remember, we have to convert temperatures to Kelvin. Kelvin equals degrees Celsius plus 273.15. So now T1 equals 372.15 Kelvin, and T2 equals 353.15 Kelvin. 2,800 meters cubed divided by 372.15 Kelvin equals V2 over 353.15 Kelvin. Solve for V2. Multiply both sides by 353.15 Kelvin. 353.15 Kelvin times 2,800 meters cubed divided by 372.15 Kelvin equals V2. V2 equals 2,657 meters cubed. Here's another example. At 0 degrees Celsius, a gas occupies 22.4 liters. How hot must the gas be, in Celsius, to reach a volume of 25.0 liters? V1 over T1 equals V2 over T2. Remember, we have to convert temperatures to Kelvin. Kelvin equals degrees Celsius plus 273.15, so T1 equals 273.15 Kelvin. Substituting in what we know, 22.4 liters over 273.15 Kelvin equals 25.0 liters divided by T2. Solve for T2. I like to cross-multiply here. 22.4 liters times T2 equals 273.15 Kelvin times 25.0 liters. T2 equals 273.15 Kelvin times 25.0 liters divided by 22.4 liters. T2 equals 304.9 Kelvin. Convert to degrees Celsius. Celsius equals Kelvin minus 273.15, so T2 equals 31.7 degrees Celsius. There are other gas laws.